Hello. In this video, we will cover section 3.2, which is on the empirical rule and z-scores. The empirical rule is a rough guideline for measuring variability. The rule says that if the distribution is unimodal and symmetric, then approximately 68% of the observations will be within one standard deviation of the mean. Approximately 95% of the observations will be within two standard deviations of the mean. And nearly all observations will be within three standard deviations of the mean. We can use the particulate matter example from the previous section to illustrate the empirical rule. In that example, the particulate matter was measured in 371 cities. The mean was measured at 7.9 micrograms per cubic meter, while the standard deviation was 2.2 micrograms per cubic meter. We can create boundaries for the number of standard deviations from the mean by adding and subtracting the standard deviation from the mean. So to find one standard deviation from the mean, we take the mean and subtract a standard deviation, and that gets us a boundary that is one standard deviation below. We can take the mean and add a standard deviation, and that gets us a boundary that is one standard deviation above the mean. We can repeat that, except with two standard deviations, so take 7.9, take the mean and subtract the standard deviation twice, and that gets you a lower boundary for two standard deviations below the mean. Take the mean and add the standard deviation twice, and that gets you a boundary for two standard deviations above the mean, and then so on for three standard deviations. And then what the empirical rule says is that once we've got boundaries for one standard deviation, then 68% of the data in the data set should lie within one standard deviation. 95% of the observations in the data set should lie within two standard deviations, and nearly all of the observations in the data set should be within three standard deviations. We can check to see how well the empirical rule works by comparing the number of observations that should be within the given boundaries to the actual number. All right, so here we have a distribution, the particulate matter distribution problem, and then we've gone through and marked one standard deviation below the mean. So here's the mean, one standard deviation below, one standard deviation above. The empirical rule says that we should have 68% of the observations should be within that one standard deviation. So how many is that? Well, if you go ahead and take 68% and multiply by how many there are, then that tells us there should be 252. If you actually look at the observations themselves and you go through and count them up, you can't do that with the bars here, but you could if you actually had a list. You go through and have a list, and you count how many are between these two red bars, the values here at these 2 points. And what you actually get is 268. So 252 is the estimate from the empirical rule, 268 is the actual. Those are pretty close. It's hard to tell exactly how close. We'll come back to that in a minute. How about two standard deviations? So we've got two standard deviations of the red lines here. So we can go through, and the empirical rule says that 95% should be within those two bars. We can figure out how many that is by taking 95% of 371, and that's 352. And then by using a list, we could go through and just count up how many are between these two values at the two red bars here, and the actual number is 344. All right, so there's 344 actual observations that are represented by this distribution between these red lines as compared to an estimate of 352. So those are close. It's hard to tell exactly how close. Again, we will come back to that. And then three standard deviations should contain pretty close to all the observations. So all the observations is 371 because that's how many observations there are. And then the actual number within three standard deviations, which are the red lines here, is 368. So the three observations that are not within the red lines are the guys over here at the far right. Okay, so now the best way to go through and illustrate the effectiveness of the empirical rule is to translate the number of observations into a percentage. All right, so that's what all this says here. So what we can do is we can go through and take the 268 actual number, and we can turn that into a percent that we can then compare with the 68%. We can take the 344 and turn that into a percent of observations that are between the red lines, and then compare that to the 95%, and so on. Okay, and that's going to give us a better way to compare. It's just going to be easier to go through and look at the numbers to see how close a job, how good a job the empirical rule did and how close we got with the actual. And so the empirical rule says that 68% should be within one standard deviation. If you take 268 divide by 371, you get 72%. That was the 268 was the actual number of observations within one standard deviation. So the actual number is 72%. So 68% were supposed to be within one, 72% is the number that actually were. And you can see how close those are. The empirical rule did a great job there. The empirical rule says that 95% of the observations should be within 2 standard deviations. The actual number is 93%. And so that's also a great job. That's a really close estimate. And then the empirical rule says close to 100% should be within 3 standard deviations. And the actual number was 99.2%. What was that? That was the 268 or 368. The 368, if you take that and divide by 371, you get 99.2. 99.2. Pretty close to 100. So the empirical rule did a great job on this particulate distribution in terms of predicting, what the distribution would be relative to the standard deviations. All right, let's look at a homework example. So the accompanying histogram shows the number of runs scored by baseball teams for 3 seasons. The distribution is roughly unimodal and symmetric, with a mean of 686 and a standard deviation of 69. An interval 1 standard deviation above and below the mean is marked on the histogram. That's here and here. The mean itself is the blue line. The red lines are 1 standard deviation below and above. And then assume the values in each of the bins are distributed uniformly. So for example, if the leftmost line is at the midpoint, then half of the bin's values are below the line and half of the bin's values are above. So they're talking about this red line, the leftmost line. And they're saying if it were at the midpoint, if it is not, but if it were, then half of these 32 would be would be to the left of the line and half would be to the right of the line. And then the half that are to the right would be within the 1 standard deviation. Okay, so we'll come back to that in a minute. According to the empirical rule, approximately what % of the data should fall in the interval from 617 to 755, which is 1 standard deviation, and then use the histogram to estimate the actual % of teams that fall in the interval, in the 1 standard deviation interval. How does your estimate compare to the value predicted by the empirical rule? And then between what 2 values would you expect to find about 95% of the teams? So let's go through and answer those. According to the empirical rule, I'm going to repeat the question again. According to the empirical rule, approximately what % of the data should fall within 1 standard deviation? According to the empirical rule, 68% should fall within 1 standard deviation. We just answered that. All right, and then it says use the histogram to estimate the actual % of teams that fall within this interval, the red line interval. Okay, so to do that, what we need to do is first we need to go through and estimate the amount of the bars that are between the red lines, so the amount of the bars. So let's start off with this bar here from 600 to 650. How much of that bar is within the interval? All right, so just eyeballing it. Okay, so this is about half right here. That would be about half, so it's more than half, but not a lot more than half. So if half is right here, then we want a little bit more than half. So a reasonable guess is about 60%. That about 60% of this bar is within the red interval here, which represents 1 standard deviation. We can say that all of the bar from 650 to 700 is between the 2 red lines within the 1 standard deviation. And the same thing is true for 700 to 750. That's this bar here. Okay, and then finally we have from 750 to 800, and we only have a sliver of that bar. And so I said about 10% of that bar is within the 1 standard deviation interval. All right, so once you've done that, if 60% of the bar is within the interval and the bar contains 32 observations, then we can multiply the 2 and get the number of observations that would be within the interval. So 60% times 32 is 19.2. So 19.2 observations, we're saying from this first bar are within the 1 standard deviation. Next, this bar, all of it is within the interval, and we've got 34 observations there, so all 34 are within. The next one, the entire bar is within, and it contains 27, so we've got 27 more observations that are between the 2 red lines or within 1 standard deviation. And then finally, we've got 16 observations that are in this bar, and we said 10% was within the interval, so 10% of 16 is 1.6. So we're saying 1.6 of those 16 are within the interval. All right, and then finally, once you've got that, you can go through and add those up. 19.2, 34, 27, and 1.6. That gets us the number of actual observations that are between the two red lines. Using that method, using our estimate method, and that's going to total 81.8. All right, so what percent of 81.8 is what percent of the total is 81.8? Well, to figure that out, divide by the total. So the total is 2 plus 4 plus 32 plus 34 plus 27, 16, 2, and 3. That's 120. So 81.8 divided by 120 is, check that out, 68%. So this is the actual, this is not using the empirical rule. This is the actual amount that we got by estimating. And we got the actual amount that we got by estimating is 68%. And the empirical rule says that we should get what within one standard deviation? 68%. And so it is a perfect match. Okay, so the empirical rule did a fantastic job with this homework problem. Okay, and then there's a third part, sorry. Between what two values would you expect to find about 95% of the teams? So the empirical rule says that 95% of the observations should be within 2 standard deviations. And then to calculate where 2 standard deviations are, we go through and take the mean and subtract the standard deviation twice, take the mean and add the standard deviation twice. That gets us these 2 values. Those are the 2 values that give us the boundaries for 2 standard deviations. And so 95% of the observations should lie between those 2. Okay, z-scores. Z-score is the number of standard deviations that an observation is from the mean. It is interpreted as a distance. If a z-score of an observation is 1.0, then it is considered to be located 1 standard deviation above the mean. If a z-score is negative 1.4, then it is located 1.4 standard deviations below the mean. Okay, it is possible to translate all of the observations in a distribution into z-scores. That is called using standard units for the distribution. We can combine z-scores and the empirical rule to interpret the rarity of observations. From the empirical rule, we know that 95% of the observations are within 2 standard deviations of the mean. If an observation has a z-score that is between -2 and 2, then that means it is one of those 95%. Since 95% is most of the observations, we can say that such an observation would be common. Okay, so if you're between -2 and 2 standard deviations of the mean, then you're common. You're a common observation. If an observation has a z-score that is greater than 2 or less than -2, then it is going to be one of the observations that's in the remaining 5%. Okay, so if 95% are between -2 and 2, then only 5% are left to be greater than 2 or less than -2. So if you've got a z-score that is greater than 2 or less than -2, then you're in that 5%. Since 5% is a small portion of all the observations, we can say that such an observation would be rare. Okay, 5% is a small amount. And so if you have a z-score that would correspond to being a member of the 5%, then you're going to be, and that observation is going to be rare. All right, so to summarize, translate all this stuff into just a very simple rule. An observation with a z-score greater than 2 or less than -2 is considered rare. Okay, so let's look at a z-score example. So what we've got a dot plot here. It contains heights of 247 men. The average height is 70 inches. The standard deviation is 3 inches. Okay, and then so we can see that the dot plot contains the standard deviation increments in heights and in standard units. Okay, so let's go through those. So if we've got, here's the mean. So 1, if we go through and add 1 standard deviation, that's 3. Then we get 73, add 3 again, we get a second standard deviation, that's 76, 79, and then we can subtract standard deviations to get 67, 64, and 61. Okay, so what are the standard units for those? The standard unit for the mean itself is 0. That's that's the 0 distance away, 0 z-score away from 70. If you go 1 standard deviation to 73, then that's going to correspond to a z-score of 1, because you've moved 1 standard deviation. If you go a second standard deviation, then you get a z-score of 2. If If you go a third standard deviation, then you get a z-score of 3, and so on. Okay, and so we can go through and just count up z-score, count up how many standard deviations, and that corresponds to the z-score. So what does that mean in terms of this interval? So that the way that you can use that is you could say that if an observation has a z-score, has the height of 70, then it has a z-score of 0. So all of these observations, all these dots have z-scores of 0. We could say that all of these dots that are above 73 have z-scores of 1. All of these dots above 76 have z-scores of 2. All these dots above 67 have -1, 64 have -2, and so on. What about between 64 and 67? What about all these others? Well, we're going to have a formula that will enable us where you can just take a height and you can just plug it in and it will produce a z-score, but we're not there yet. And so at this point, we don't have the ability to go through and do that. You could try and estimate maybe what the z-score is by saying, okay, well, from 67 to 70, so halfway between those, that's going to be 1.5 units. That's going to be at 68.5. That would be -0.5. And then you could figure out whether these dots here are at 68.5. You could try and do that. That would be a way to go through and estimate what the z-score is for observations that are not directly on the standard deviations, but we're going to have a formula for that. So we're going to come back to that. All right, so let's talk about rarity briefly here. So the few observations with a z-score less than -2 or greater than 2 are going to be considered rare. That's what we were just saying a minute ago. And so it would be rare to have a height. So if we go through less than -2, so that's 64 inches, so that corresponds to 5'4". If you're below 5'4", and this is for men, so if you're below 5'4", then you have a rare height. And then if you are above 76 inches corresponds to 6'4". If you're above 6'4", so we do have a couple that are rare in this sample, in this data set. And then we do have a couple here that are above 76. So we do have a couple rare entries at both ends. All right, so another example, a second example, Maria scored 80 out of 100 on her first stats exam and 85 out of 100 on her second stats exam. On the first exam, the mean was 70 and the standard deviation was 10. On the second exam, the mean was 80 and the standard deviation was 5. On which exam did Maria do better relative to the rest of the class? This is another thing that you can go through and you can do with z-scores is you can compare performance over multiple distributions. All right, so what we can do is we can convert both exam results to z-scores, and then we can compare the z-scores to see which one was higher. Okay, so you take the score of 80, all right, so she scored 80 to go back, right? So she scored 80 out of 100 on the first exam, all right, and the mean was 70 and the standard deviation was 10, all right? So if you score 80 and the mean is 70 and the standard deviation is 10, then the z-score is going to be 1. You were 1 standard deviation above the mean. For the second exam, she scored 85, but that time the mean was 80 and the standard deviation was 5. So how much is 85 above the mean when the mean is 80 and the standard deviation is 5? It's 1 standard deviation above, so it also has a z-score of 1. All right, and so if you go through and kind of do this type of translation thing to compare, this comparison, obviously 85 is higher than 80, so the point of this is to compare performance with the rest of the class. Okay, so versus the rest of the class. And so versus the rest of the class, if the z-scores are the same, then Maria scored equally well on the 2 exams. So neither performance was better or worse than the other. All right, so what I was just saying a minute ago, how could you go through and translate z-scores that are not directly on the standard deviations? You can go through and use a formula. So here is the formula. So you've got the z-score equals, you take the value of the observation, you subtract the mean and divide by the standard deviation. And this says the exact same thing, just written with symbols. So x is the observation, x bar is the mean, s is the standard deviation. So I put in words, this is how I think about it, which may make it more confusing, but I'll go ahead. So what you do is you first find the distance between the observation and the mean. All right, so you go through and you take the observation and you subtract the mean, and that gets you a distance, if you want to think about that, on the distribution graph. Okay, so you go through and you figure out how far between an observation and the mean. And then you go through and you divide to figure out how many standard deviations is that. All right, so you go through and you divide by the standard deviation to determine the number of standard deviations that the distance represents. So that's how I think about it. Okay, so if you've got 2 standard deviations that your observation is from the mean, okay, then you'd first go through and you would subtract the mean from the mean from the observation, and let's say that gets you a distance of 10, okay, and then the standard deviation is 5, then 10 over 5 is going to give you 2, so you get 2 standard deviations. Okay, another example here. So the mean daily temperature in San Francisco is 65 degrees. Standard deviation is 8. On one day, the high temperature is 49 degrees. Convert the temperature to standard units by finding the z-score, and then assuming the empirical rule applies, is this temperature unusual? Is it rare? They're asking a rarity question. So they want us to use the rarity stuff that we've been working on. Okay, so to go through and translate the observation into a z-score, you go ahead and subtract the mean from the observation. So we've got, this is the observation, this is the mean. You subtract, you get -16. And then how many standard deviations is -16? Well, a standard deviation is 8, so -16 over 8 is 2. So there's 2 standard deviations. All right, and then you can also use the formula here. If you don't like the way that I do it, maybe it makes it a little bit simpler. And then once you've got that, so 2 standard deviations. So would this be considered unusual? It would be considered unusual. It would be considered rare, since a temperature this cold or coldly only occurs 5% of the time. Okay, so if you're below 2 standard deviations or above 2 standard deviations, then you're in that 5% gap. Hopefully that makes sense. All right, and then assume that women's heights have a distribution that is symmetric and unimodal with a mean of 66 inches. Oh, by the way, this is a homework example. I just jumped right in. So assume that women's heights have a distribution that is symmetric and unimodal with a mean of 66 inches and a standard deviation of 2.5. Assume that men's heights have a distribution that is symmetric and unimodal with a mean of 75 inches and a standard deviation of 1.5. And then answer the questions. So what women's heights correspond to a z-score of -1.8? So this is asking you to start off with a z-score and find a height. So we haven't done that up to this point. So I'll show you how to do that. And then a professional basketball player, Evelyn Akator, is 75 inches tall and plays in the WA and NBA. Meanwhile, professional basketball player Draymond Green is 79 inches tall and plays in the NBA. And then basically it's saying which has a higher z-score. All right, so first, how do you translate from a z-score to a height? You start off with the formula. So there's the formula, z-score equals value, the observation value minus the mean over the standard deviation. And then you just want to plug everything that you know into that. So you know the z-score, that's going to be -1.8, so put that here. You know the mean, so plug that in and put that here. You know the standard deviation, so plug that in, put that here. So you've got the value is the unknown, right? So this is going to turn this into an algebra problem. So we've got -1.8, that's here, equals value, that's the unknown, minus the mean, which is 66, over the standard deviation, which is 2.5. And then you just want to solve from there. So to solve this algebra problem, you multiply both sides by 2.5. That gets you this. And then you add 66 to both sides, and that gets you this. All right, and so the height that is equivalent to a z-score of -1.8 is 61.5 inches. All right, and then first we need to go through and find, so this is the question part B, who has a higher z-score, Evelyn or Draymond? And so to go through and figure that out, we use the formula. So z-score equals, so Evelyn's height was 75, minus the mean, which was 66, over the standard deviation, which is 2.5, and that turns into a z-score of 3.6. And then for Draymond Green, we get 79 minus 75. So Draymond Green's height 79 inches. The mean for men is 75. The standard deviation for men is 1.5. And so we get 2.67. So at least comparing to their peers, Evelyn is taller than Draymond Green, using that standard. So obviously Draymond is taller just in terms of 79 versus 75, but compared to their peers, Evelyn is taller. Okay, I believe that is it. Yep, that is the end of the slideshow. So thank you for watching. I will see you next time. Bye-bye.